Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone. Welcome back to our class. Today we're going to learn compounds with metal to carbon sigma bonds. So before this we have learned the structural characterization of organometallic compounds. Today we are going to see in details the type of metal to carbon that we can have in our complexes. It can be in the form of metal alkyls, metal aryls, and so on and so forth. Now, we know that organic compounds they are capable of making sigma bonds with metal centers are alkyls, meaning it can be any alkyls, it can be methyl, phenyl, acyl, and so on and so forth. So let us see the first one, metal alkyls. The alkyls that are able to bond with your metal stably would be alkyls with no beta hydrogens. For example, we have methyl, benzyl, nobonyl, neopentyl, and trimethyl, silyl methyl, JMS. So from the structure, I hope we do understand, we have a common understanding that there is no beta hydrogen here. So if you don't remember, let me refresh here. Beta hydrogen, for example, if your metal is attached to this carbon, there is no such thing as beta hydrogen because this is the only carbon that you have. The same thing for this one, even though we have the next carbon here, metal is here, attached to this carbon, this is the alpha carbon, but this beta carbon will not have any hydrogen. And let us see neopentyl. If your metal attached to this carbon, so your beta carbon also has no hydrogen. So there is no beta hydrogen in this alkyl. Why we don't want any beta hydrogen? Because we want to form stable complexes with transition metal. If you have beta hydrogen, then it is very likely for the metal complexes to undergo a process which is called beta hydride elimination. So we do not want this to happen because this will form a unstable complex. So let us look at this mechanism. You can see that we have alpha carbon here and beta carbon here. This is alpha because this is already attached to your metal. So your second carbon, your beta carbon now has one hydrogen. So this is beta hydrogen. If you do have this, then it is very likely for this hydrogen to be eliminated. And when that happens, this eliminated hydrogen will form complex with your metal, and this metal hydride is unstable. So we do not want that to happen. The same thing for this second example. With beta hydrogen here, we are going to be forming metal hydride, which is also unstable complex. So we do not want any unstable complexes to be formed. So that's why for alkyls to be able to bond with your metal with a stable configuration, with a stable complex, we need to make sure that your alkyl do not have any beta hydrogen that I have mentioned earlier. I hope you are clear on this particular part. Now moving on. So the mechanism shown indicates a four-center transition state in which the hydride is transferred to the metal. Okay. So the beta hydride elimination reaction is made possible by the presence of. So there are ways where beta hydrogen elimination can take place. The first one, when you have a vacant coordination site on the metal, meaning your metal has different angles to which your ligand can coordinate to. So we need to make sure whether there is a vacant coordination site on the metal or not. If there is, then bulky groups such as neopentyl and TMS block attacks or at all transition at all coordination positions. So thus stabilizing metal alkyl. So this is called stabilizing by steric crowding. So we need to have bulky structure like neopentyl attaching to your metal. So when this happens, there will be a steric hindrance, or we call it a steric crowding. We are crowding the metal, so we are blocking all the coordination sites. So we are going to stabilize the metal alkyl. The second one, a vacant orbital on the metal. So which to interact with the beta carbon beta hydrogen bond, which is only available in transition metals, not main group metals. So you can see a vacant orbital on the transition metal. So when you see this, then you will not be stable. It is stable when you have main group alkyls because it does not have a vacant orbital on the metal. For example, we have green regions, we use magnesium here. Magnesium is a stable main group. So there are two ways where beta hydride elimination reaction is possible. If we have vacant coordination site on the metal, so therefore we need to have bulky group just to make sure to protect all the coordination sites from being attacked. So this is called stabilizing by steric crowding. Or we can have a vacant orbital on the metal. Normally these can be seen on the transition metal. So that's why normally as more stable complex can be found in those main group complexes. Okay. Now alkyls are good sigma donors. So that's why they are capable of stabilizing high oxidation states of metals. So they are giving electrons to the metals, high oxidation state of metal, for example, cobalt 4 and also cobalt 5. So the first part of this lecture, I just want you to understand that alkyls, metal alkyls can be formed, but you must make sure that those alkyls are not having any beta hydrogen. Else, we could undergo a process which is called beta hydride elimination. When this happens, your complexes are going to be unstable. So moving on, second type is metal aryls. Aryls when we are using benzene here. So metal aryl complexes also tends to be stable. Why? Because it does not have any beta hydrogen. So if it does have beta hydrogens, it is going to undergo beta hydride elimination. Even if they have a beta hydrogen elimination, beta hydride elimination might not be that likely to happen. Why? First one, because in order for that to happen, the metal, the alpha carbon, the beta carbon need to be coplanar, which is impossible because this will make your this will be hindered by the ring strain, because it is very impossible for us to have a metal alpha carbon and also alpha beta carbon to be coplanar. Okay, and the second one, if beta hydride elimination takes place, it will destroy the aroma TCT, which is not likely because this comprises the stability of the ring. Okay, meaning the ring will be totally damaged. So the most common aryl, definitely we have seen this phenyl C6H5, and the symbol is BH. So we can see these are the examples of phenyls bonded to a metal. So aryl rings have pi donor substituents. Are shown below. Okay, we have this is phenyl, this is a metal, this is the other ligand, and this phenyl is attached with one substituent. We call it pi donor substituents. So these pi donor substituents are able to donate the electrons to the phenyl, to the metal. Now your substituent will become slightly positive and your metal will become slightly negative. And pi back donation will be likely to happen. And second aryl also capable of accepting electrons from metal, definitely. So through pi back bonding, this is the basic formation of any metal complex. First, there will be donation from ligand to your metal, and then your metal, since it is a positive by nature, will be giving back the electrons to your ligand. So you see here, this is defining without substituent. We can see that metal is actually able to give the electrons to your phenyl. So phenyl is conjugate bond can alternate. So your metal can give the electron to your phenyl, making phenyl actually negative. This is called pi, and the bonding, tight combination. Okay, nothing fancy here. So there are two types. We have methyl alkyls and we have methyl aryl. The main point here that I want to deliver is about the beta hydrogen, whether it is presence, whether it is absence. So the presence of beta hydrogen will make your complexes undergoing a process which is called beta hydroamination, making your complex to be unstable. Now moving on to the second part of the lecture on the compounds with multiple metal carbon bonds. So we are going to see two types, metal double bond C or metal triple bond C. So the first one is metal double bond C. We call it carbene or alkylidynes complexes. So there are two forms of carbene. This one also carbene, this one also carbene because it contains an double bond C. But this one is called Schrock type carbon because it consists of R alkyl groups directly attached to your alpha carbon. And this is called Fischer type carbene, also carbene, but we call it Fischer type carbene because your alpha carbon is being attached with E. E is actually electronegative atoms such as your oxygen, sulfur, and nitrogen. Only then this E is bonded with R or any alkyl or aryl group. So alkylidine ligands usually have alkyl substituents, as I said, and carbene, Fischer type carbenes have heteroatom substituents. Okay, so we have Schrock type alkylidyne, we have Fischer type carbene with heteroatom. Okay, now look at this. Alkylidynes or Schrock type carbenes contain only carbon and hydrogen attached to the carbene bond. So first synthesized several years after initial Fischer carbene by Schrock groups. Fischer is the one that founded the carbene compound, and then later this Schrock's research group work on the second type of your carbene, which is your Schrock type of carbene containing alkylidyne. Now this table summarizes the explanation that I have given earlier just now. So for oxidation state, for Fischer it involves low oxidation state. For Schrock, it involves high oxidation state like titanium and thallium. Yeah? We have 4 and 5 here. This one 0, 0, and 0. Substituents attached, as I said earlier, for Fischer, heteroatoms, very electronegative atoms, oxygen, nitrogen, and sulfur. And for Schrock type, it's normally attached by hydrogens or alkyls. Other ligands normally attached by pi acceptors. This one can be sigma or pi hydrogen. So electron count for Fischer must be 18, but for Schrock type it can be 10 to 8, but it is still stable. So Fischer carbenes are typically found on electron-rich, low oxidation state metal, as I said earlier. Okay, mid to late transition metal. The presence of heteroatom on the alpha carbon, the presence of heteroatom like this one on the alpha carbon, allowing us to draw a resonance structure, meaning your double bond from carbene M to C can shift to this part, to carbene to heteroatom part. So making your metal slightly negative and your heteroatom slightly positive. So if you look at this molecular structure properly, one lone pair from your carbon is donated from the carbene to an empty orbital of your metal, and then filled metal orbitals will be giving back the electrons to your carbene. Okay, back donated to your carbene, involving PZ orbital. Okay, the blue one. So we have two steps. Definitely the donation from ligand to metal, and then from metal back to your ligand. So there is competition for this backend orbital by the lone pairs on the heteroatom. So as what we have shown in the second resonance structure. Okay. So this body closely resembles of carbon monoxide. If you don't understand CO, then you could would definitely understand this well. So since it has quite a resemblance to your carbon monoxide, it is being considered as neutral species. For Fischer carbenes, it is considered as neutral species, unlike dianionic Schrock alkylidynes and ionic dianionic, meaning it is an ion. Schrock, that one is not neutral species. Okay, the Fischer type carbene complexes usually more stable than Schrock. Okay, why so? Because we have highly electronegative atoms like oxygen, nitrogen, or sulfur, and then these can participate in the pi bonding. So which results in the three atoms. Pay attention here. We have d orbitals on the metal. We have d orbitals on the metal, and we have p orbitals on the carbon or carbene, and then we have p orbitals on the electronegative atom. So this is a very stable configuration. So such delocalized three-atom system provides extra stability to the pi bonding pi electron pair than the normal metal to carbon pi bond. Okay, so Fischer carbene is more stable than Schrock because it does have a highly electronegative atom. So we have three atom pi system from metal orbital to your p orbitals of your carbene and the d orbitals of your electronegative atom. The metal double bonds in these complexes tend to be longer than the typical MC double bonds. Okay, you can compare any M double bond C with this M double bond C, and you will see that this type of carbene will have longer bond than the normal one, but it will be shorter than the single bond. Okay, definitely, because if we rank the length of your bond from single, double, and triple, your triple bond will have the shortest bond, and then your single bond will have the longest bond. So likewise, the CE bond, C carbon, E is a electronegative atom, is somewhat shorter than the typical ME bond. The typical ME bond will be longer than this. So look at this structure. We can see that normal CN bond is 145 picometer. Okay, we have chromium, we have C here, and we have O. This is Fischer carbene, and we have N. This is also Fischer carbene. The stronger the pi donor on the carbon, the stronger the pi donor. The stronger the pi donor ligand on your alpha carbon on the carbene itself. The lower the MC bond order. Okay, the stronger the pi donor atoms, the lower the MC bond order. Thus lower the barrier to rotation around MC bond. So I hope you are clear with this. We have learned this before this on the relationship between bond order, bond length, bond strength, and the strength of your ligand. So we have seen the first part of carbene. The second part will be on the M triple bond. Next, we are moving on to the M triple bond C. We call it carbene and alkylidyne complexes like alkene, alkylidine, alkyne, alkylidyne. Okay, so we have carbene and alkylidyne complexes here, which are of course related to carbene and alkylidyne complexes. So how do we get your carbene? So you have carbene here, M double bond C. We have to remove heteroatom. This methoxy OME. We remove this one. We are going to get a carbene. Okay, so like this one. So your methoxy removed, combining with this BBr3, and you're going to get your carbene here. So you see CR triple bond with your C. So from carbene to carbene, you need to remove heteroatom subunit. So from the X-ray data, we can see that definitely the CRC bond distance in carbene is 204 longer than that of CRC bond in the carbene. So your alkyne will have a shorter bond than the alkene. The carbene will have a shorter bond than carbene. So for Schrock type alkylidyne complex, we can get your alkylidyne complex from alkylidyne. How? By remove alpha hydrogen. We have a metal here. This is your alpha carbon. So we can remove one alpha carbon, one hydrogen here. So you're going to get beta alpha hydrogen. Sorry, alpha hydride elimination, and then you remove this holding, you are going to get this structure. So why this is CME4? Because this is initially CME3. So this CH2 will take one hydrogen from here, will form another methyl, CH3. So 3 plus 1 methyl, you're going to get 4 methyl, CME4. So from the structure here, you can get your alkylidyne complex. So why do we use this ME3? Because we want to impose or increase the steric crowding. Remember, the steric crowding is used to stabilize your complex. Only then we can remove the alpha hydrogen. Okay. So this is the metal triple bond is short as expected, as I said earlier. So we compare the triple bond with the single bond. The triple bond is 169, single bond is 194. Much longer than your triple bond. So the summary of your sigma bond type, easy. We have learned this repeatedly in some other courses as well. So you can see alkyl M2C, 1 sigma bond, aryl 1 sigma bond, M2C. Yeah? I'm talking about M2C. And carbene, we have double bond, so 1 sigma, 1 pi bond. Alkylidyne, we have 1 double bond, so 1 single bond, 1 sigma bond and 1 pi bond. Carbene and alkylidyne, we are going to have triple bonds, so 2 pi bonds and 1 sigma bond. The only things that might be I don't think it is heavy. It's easy for you to remember. The alkyl 2 electrons, aryl 2 electrons, carbene 2 electrons. We have seen in fact some of these ligands before this in the previous tables. And then your alkylidyne will donate 6 electrons. Okay, the more exercises that you will do, the more easily this can be remembered. Okay, that's all for now. See you in the next video. Thank you for your kind attention. Assalamualaikum.